Assalamualaikum and good afternoon. Today, my group for electrical principle 1, group 4 will be presenting our project. My group members consist of 5 persons, which is Muhammad Afiq Najmi bin Muhammad Najib, holding matric number 240139, Muhammad Luqman Nul Hakim bin Hashim, holding matric number CN240267. Then Muhammad Faik Haikal bin Nazri, holding matric number 240437. Then Muhammad Suleiman Muhammad Adam, holding matric number AN240195. And lastly, myself, Muhammad Danish Furkan bin Muhammad Faisal, holding matric number CN240304.
Assalamu alaikum. We are in group 4. We will present about a non-inverting amplifier. A non-inverting amplifier is a fundamental operation amplifier configuration that amplifier input a signal while maintaining it first, making it ideal for application requiring high input, impedance, and a signal integrity. This configuration allow for a positive voltage gain, which can be set by the ratio of two resources in feedback loops, ensuring maintenance desoring and high fidelities in a single process. Additionally, non-inverting amplifiers are widely used in a voice electronic application, including audio process sense signal conditioning. The voltage fluid circle due to their ability to insert the input source from the output loop while providing a suitable and reliable amplification. This simplicity and electricity making them circle component in modern electronic design.
So for the circuit diagram we use, which is non-inverting current amplifier. So from the textbook, a non-inverting current amplifier is portrayed in the figure below. So we calculate the current gain. So the R1 is given 8 kilo ohm and the R2 given is 1 kilo ohm. So below, which is using software, which is one of my teammates using multisim software. So we apply the circuit from the textbook and we apply to the multisim. So the amplifier code was M741CN. We use the amplifier for this project.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Faik Haikal bin Nazri and my matrix number is CN240437. So I will explain about the calculation. So as you can see here, first we need to calculate the voltage at node V. V positive. So V positive equal to IS times to R1. So IS is 1 milliampere times with R1 which is 8 kilo ohm. So the answer for V positive is 8 volt. 8 volt. And then we need to calculate the voltage at node V negative. So V negative equal, the value of V negative is equal to V positive. So the value of V positive that we got up there is 8 voltage, 8 volt. So V negative equal to 8 volt. And then we need to calculate the current gain. So here is the formula for current gain, which is I0 over IS equal to 1 plus R1 over R2. And then to calculate the current gain, we substitute the value of R1, which is 8 kilo ohm, and R2, which is 1 kilo ohm, in the equation. So I0 over IS equal to 1 plus 8 kilo ohm divided by 1 kilo ohm. So the value of the current gain that we got is 9 milliampere. Next, in the simulation result, as we can see here, we use multisim to search for the result. So we using 5 multimeter. As you can see, the first multimeter we got 9 milliampere as the current gain. And then as you can see, for multimeter 2, 3 and 4, we got 8 volt for each of the multimeter here. And then for the multimeter number 5, at the node here between R2, R3 and R1, we got 90.006 nanovolt. That's all for me. Thank you.
Okay, I will continue to the simulation. The objective of the simulation is to analyze the behavior of the operational amplifier circuit in multisim, focusing on voltage and current measurement using a LM741CN operational amplifier, with the purpose of validating the gain equals 9 as per theoretical calculation. The component used in this circuit is the circuit used an LM741CN operational amplifier U1, powered by dual DC voltage source V1 and V2 set to negative 12 volt and plus 12 volt respectively. It includes 3 resistors, R1 and R2 with values of 1 kilo ohm each, and R3 with a value of 8 kilo ohm. A current source I1 set to 1 milliamp is connected to the inverting terminal of the op-amp. Then 5 multimeters, which is XMM1 to XMM5, are used to measure current and voltage at various points in the circuits. So we're going through the circuit design description. The circuit is designed to analyze the behavior of the LM741CN operational amplifier in a feedback configuration. The op-amp is powered by a plus-minus 12 volt supply. Resistor R1, R2 and R3 are configured to establish the desired gain and feedback properties. The current source I1 provides input to the inverting terminal, while the non-inverting terminal is connected to a voltage reference. Multimeters are strategically placed to measure current and voltage across the circuits. Then we go into the measurement configure. The measurement are configured as follows. XMM1 measure to current supplied by I1, set 1 milliamp. XMM2 and XMM3 measure the voltage at the non-inverting and inverting terminal at the op-amp respectively. XMM4 measure the output voltage of the op-amp, while XMM5 measure the voltage across the resistor R1. Then we go into the step to perform the simulation. To perform the simulation, open multisim and click New Project. Place the LM741CN op-amp, resistor R1, R2 and R3, and the DC voltage source V1 and V2 in the workspace. Add the current source I1 and configure it to 1 milliamp. Insert 5 multimeters and connect them to the circuits for measuring the desired parameter. Wire the component carefully, ensuring proper polarity for the voltage source, set the multimeters to measure the required parameters. A for current, XMM1, and V for voltage, XMM2, XMM3, XMM4, and XMM5. Once the setup is complete, run the simulation by clicking the run buttons. Let's go into the simulation observation. The simulation result are as follow. XMM1 measured to current 9.001 milliamp through the circuit, indicating consistently supply current. XMM2 measured a non-inverting terminal voltage of 7.99 volt, while XMM3 measured an inverting terminal voltage of 8.001 volt. XMM4 shows an output voltage of 8.001 volt, consistently with the inverting terminal voltage. XMM5 measured the voltage across R1 of approximately 90 nanovolt. It might equal to 0 volt. So the analysis of this simulation, the small voltage difference between the inverting and non-inverting terminal highlight the high input impedance, low offset voltage of the LM741CN. The output voltage matched the expected value, and the gain, calculated as VO over VI, is confirmed to be experimentally 9, consistent with the theoretical expectation. The measured current through I1 and the voltage across R1 further validate the circuit performance. So, the conclusion of the simulation, the multi-sim simulation successfully demonstrate the operational characteristics of the LM71CN of M in a feedback circuit. The measurements obtained are consistent with the theoretical calculation, confirming that the circuit gains equal to 9 as designed, theoretically validating the circuit setup and designs.
So this is the hardware results. So the equipments, we use a breadboard, 9 volt battery, potentiometer which is we set to 8 kilo ohms, and 2 1K resistor, jumper wire, and analog multimeter. So after we do the hardware test and we get the results, the analog multimeter readings result shows that the current in the circuit is at 9.3 milliamp. So now I will present an analysis of an inverter operational amplifier circuit simulated using the LM741CN operational amplifier. This circuit uses an inverting configuration where the non-inverting input is grounded, and the virtual short principle ensures the inverting input is maintained at approximately 0 volt. The input current set at 1 milliamp flows through a feedback network comprising R1 equals 1 kilo ohm, R2 equals to 1 kilo ohm, and an input resistor Rin equals to 8 kilo ohm. The theoretical closed loop gain is calculated as AV equals RF over Rin equals to negative 2K over 8K equals to negative 0.25. Meaning the output voltage is inverted and reduced by a factor of 4 relative to the input voltage. In the simulation, the multimeter displayed an output current of 9.001 milliamp, matching the expected value. This result reflects the sum of the input current I1 equals to 1 milliamp and the feedback current calculated as IF equals V out over R1 plus R2, which is equals to 2 volt over 2K equals to 1 milliamp, alongside the input current contribution of 8 milliamp. Together, this aligns with the circuit's design and confirms its theoretical behavior. In hardware testing, the multimeter showed an output current of 9.3 milliamp, slightly higher than the simulation results due to resistor tolerance and the actual power of 9 volt battery measured at 9.7 volt. Despite minor difference, the results validate the circuit's functionality, demonstrating the accurate closed-loop gain and current flow of the inverting amplifier. This analysis highlights the effectiveness of the feedback network in achieving predictable op-amp behavior and reinforces the importance of understanding feedback design for reliable amplifier performance.
In conclusion, the project design analyzed a non-inverting current amplifier of gain 9. Standing formulas were used for the calculation, which approved the theoretical gain. A simulation and experimental implementation of the above statement was done. Simulation were given as close to theoretical calculation as much as possible. Experimental management management matched both theoretical and simulated value. The project provided how theoretical knowledge needed to be applied to real-world practical experience and also the solution important to provide a design for overcoming a problem in real-world hardware. Eventually, the project objectives were related to practically applied to the theory of the non-inverting current amplifier in electrical engineering.